Hello everyone, my name is Scott and welcome to the third tutorial on basic electronics, and today we're going to cover the color bands of resistors. Let me just actually show you a few. This is a fixed value resistor. You'll see a lot of these. This is a LDR, light dependent resistor. We'll be using these in our projects. This is a trim pot potentiometer. That's also a variable resistor. We adjust the resistance using a screwdriver. And these, of course, are our fixed value resistors with our color codes, which we're going to do briefly. This is an LED. Oh, by the way, these have no polarity. It doesn't matter which side you put positive, which side you put negative. These, of course, have polarity. This is an LED, and the longer end, notice how the ends they're almost the same size, but the longer end would be the positive side, and the shorter end would be the negative side. And let's say you took this component out of a previous board and wanted to reuse it. Well, there's another way to tell an LED. On the negative side, this is round all the way around, except there's a flat side right here for the negative. This is an electrolytic capacitor. The long side, of course, is positive, and the short side is negative. And you can't see it here, but there's a blue field with a bunch of negative symbols running down the side, which is also another indication. And you'll see that in future labs and videos. I just thought I'd point those out. Well, this is a larger electrolytic capacitor. Same thing applies. And actually, see, you can see the negative symbols here. Negative, negative, negative. Short leg is negative. And we'll show you how to put those into your circuits. But right now we're going to talk about resistance, and we're going to talk about Ohm's law. Now, at the beginning I told you this is a practical course in electronics, and we're not going to delve into a lot of theory, which we're not, and we're not going to do a lot of math. We're only going to do the math necessary for us to actually build things. A little bit of the math involved, one thing we do need to learn is Ohm's law. And what Ohm's law does for us is tells us whether we can safely put a component into our circuit, or what we need to actually safely put a component into our circuit. It also tells us a lot of things. It tells us how much power we need, or how much amperage we need to power our circuit. It tells us many things. And let's actually just get into it instead of talking about it. First, we're going to deal with the color codes for resistors. Okay, you have 4-band resistors and 5-band resistors. Let me get a pen here. And you can get these color codes anywhere on the internet. They usually come when you buy packs of resistors, so it's everywhere, this color chart. So you can use this color chart, or you can memorize this chart. And there's a simple way to memorize it, and I'll show you that shortly. Anyways, this is a 4-band resistor. This is a 5-band resistor. 99% of the resistors you're going to deal with are 4-band resistors. In the last band on both of these is for tolerance. The first 3 bands of this 4-band resistor determine the Ohm's value, and the first 3 bands of this 4-band resistor determine the Ohm's value, and the first 4 bands of this 5-band resistor determine the Ohm's value. Now, how do we determine the Ohm's value? Okay, like I said, the easiest way to do this, or to figure this stuff out, is to just do it. So we have a resistor here, and there's a little cheat going on here. This is a 560K ohms resistor, or 560,000 ohms resistor. Actually, before we get into it, let me mention that you'll see K used. I need some color, I guess. K is for 1,000. So a 470K resistor is actually 470,000 ohms. That's the omega symbol for ohms. It's its resistance value. Now a 10K, of course, and that's a very common resistor, would be 10,000 ohms. And 1M would be 1 million ohms. So when you're looking at these, and when you see parts lists, it'll come like 560K. It won't say 400, or 560K. It won't say 560,000 ohms. And of course, a 470 ohms is just that. 470 ohms is just that. 470 ohms. Or down here, 237 ohms. Okay, now let's get into it. So the first two bands. So the first three bands determine the value. The first two bands are just numbers. So green is 5. Blue is 6. And the third band is the multiplier. So yellow is, you'd multiply it by 10,000. But you don't have to think of it that way. That's a little difficult, you know. Think of it as the amount of zeros you want to add. 4, yellow is 4, so add 4 zeros. 1, 2, 3, 4. And that's 560,000 or 560K. So if this stripe was black, you would add 0 zeros. You wouldn't add any zeros. As a matter of fact, we're going to run into that down here. So these are the numbers of zeros you add. If you want, it's a multiplier. You can multiply it by these and you'll get the same number. Or you could just add those zeros. Okay, sorry about that. That was the telephone ringing. Where was I? We had, okay, 560K. So, we were dealing with the multiplier. So you can multiply it if you want, times 1,000, times 100, times 10, times 1. So if, 237 times 1 is 237, or you just put no zeros. Okay, so let's work with this 5-band. Our main focus is the 4-band, but we will do the 5-band, so just understand it. Now, in a 5-band, the first 3 are numbers, and the 4th is the multiplier. So let's do this one quickly. So we have red, which is 2. And I seem to have lost my color. Red, which is 2. Orange, which is 3. Violet, which is 7. And black, which is 0, or times by 1. So 237 times 1 is 237. Or you add 0 zeros. It's 237 ohms. If that was red, we would add 2 zeros. If it was orange, we would add 3 zeros. Now the tolerance. This last band here, I'm not going to talk too much about that. This is gold. I thought this was brown at first. But gold is 5% and silver is 10%. So basically on 237 ohms, and I can't really, that almost looks like, I think that's supposed to be gold. It almost looks like it's brown here. It might be. Yeah, it is brown. It's 1% brown. Let's assume this was gold, so we can do 5%. 1% is too easy. So 5% would be, we'll call it 12 ohms. So this could be plus or minus 12 ohms. If you want an exact reading, you'll have to put it to a multimeter, which we will do during the lab portion of this. We're actually going to have our first lab after on our next session. So, but as you increase the number or increase the value of ohms, that goes up greatly. So this is, I think it's 11.85. We'll just call it 12 ohms, plus or minus. And for 560,000, and I'm not doing this, I have a calculator, I'm not doing this off the top of my head, by the way, is 28,000 ohms, either way. Use your calculator, you got them. You're not in school, I'm not grading you. I use it when I need it. And we're going to be using it when we talk about Ohm's law, as a matter of fact. So this could be plus or minus 28K. So if you really need, if you can't take the variance in your circuit and you really need to lock it down to a fixed value, you can use your multimeter. But in most of my circuits, I've never needed to be that accurate where, you know, a 5% variance was going to kill my circuit. Okay, so let's do some more of this. Now let's say we know that we need a 470 ohms resistor. So now we just looked at resistors and we could tell what they were. Now we're going to have to go into our parts bucket and look for a 470 ohms resistor. Well, what colors are we looking for? Okay, well, I can tell you right now it's probably going to be a 4-band resistor. So the first 2 bands we're going to need 4, which is yellow. Actually, let's do it this way. So it's going to be yellow. And 7 is violet. And it's 470, so we have 1 0, or times it by 10, which is brown. This brown really doesn't look like brown, but and neither does this one. So our color bands would be yellow, violet, brown for a 470 ohms resistor. And gold. Well, we'll use the same color for that. And assume this is gold. And so you would be looking for a yellow, violet, brown, and we're actually going to use a 470 ohms resistor in our first circuit. And we're going to actually see in this tutorial how we figured out to use a 470 ohms resistor. So now this is the reverse. We figured out the colors we're going to look for in our parts bin to find our 470 ohms resistor. Let me go back here and put 470 ohms resistor. By the way, the larger the number, the more resistance. Well, the more voltage. When you see when we actually start testing this, the more voltage that this resistor will absorb, and the more protection it offers your circuit, the less electricity that will flow through it. Okay, so that's a 470 ohms. Now, I have some resistors here. Oh, let me mention one thing before we go out there. One of the tricks I use to you know, you can memorize the chart if you want to. I'm sure you can think of some kind of acronym to go along with all these here. I think I learned one in school. I don't remember it offhand. What I do remember is these colors go from, you can think of, first of all, from red to violet is the rainbow. Those are the colors of the rainbow. It goes red, orange, yellow, green, blue, violet. If you think of a rainbow, that's the order of the colors in a rainbow, or the frequency of visible light, the spectrum of visible light. It goes from red, orange, yellow, green, blue, violet. So that's the rainbow. Outside the rainbow, you go from darker to lighter. You go black, brown, gray, white. So dark to light, and then the colors of the rainbow. So black is 0, brown is 1, red is 2, orange is 3, yellow is 4, and right now my fingers are going up as I'm counting. I'm using my fingers to count, and that's okay, to figure out what these values are. So let's actually do that. We're going to remove this chart. You can find it anywhere on the internet. There's a ton of them. Usually when you buy packs of variable value resistors, it usually comes with one. But let's go, sorry about that. Let's go to these resistors. Now you can't see this on the video because I know I can't see it, but this is yellow and this is yellow. This is red, red, brown. This is brown, black, orange, and this is brown, black, green. Okay. So let's figure out what the values of these resistors are. Let me just make sure I'm recording after that pause with the telephone. Yes, I am. Okay. So these two are yellow, so we have yellow. We have black, which is 0, brown, which is 1. Then we follow the rainbow. Red, orange, yellow. So what I did was I was holding up my fingers as I was counting off the colors. So that gives me a 4. Black is 0, brown is 1, red is 2, Orange is 3, yellow is 4. So that is 4. Violet. It's not blue, it's violet. Once again, we have black, brown, which is 0, 1. And then we have red, orange, yellow, green, blue, violet. And that's 7. And you can't see me, but my fingers were going up as I went through the colors, and that's how I got it. That's how I figured it out. It was 7. And then, of course, we have yellow again. We don't need to do that. But, yes, we do, because it's not 4. We don't put a 4 here. That's our multiplier. So we can go back here. Well, basically, we could add 4 zeros. But, you know, if you wanted to, for those of you who are sticklers, you can use your multiplier and you multiply it by 10,000. And what happens when you multiply it by 10,000? You add 4 zeros. And gives us 470K. 470K ohms. Because you won't hear people refer to this as 470,000. You'll hear 470K ohms resistor. Okay, so now we have red, red, brown, and a gold is the 5% tolerance. We're not going to do if you want to do the 5% tolerance, you just multiply 470,000 times 0.05, and that'll give you the variance that you can add or subtract to this number. Like I said, I don't want to get heavily into math we don't need to get into. There's going to be a little math later on, and we're going to minimize the math. It's all going to be basically, you know, multiplication and division, and feel free to use your calculator. Okay, so red. We have black, brown, which is 0, 1, and then red. So that's 2. Red again, which is 2. I don't need to use my fingers again. And then brown. Black, brown. This is our multiplier. Now, so I don't put 1 here. I actually put 1, 0. If we come back to here, you see brown is 1, 0 or times 10. $22 times 10 is 220 ohms. No K, no M after that. So this is a 220 ohms resistor. Now we have brown, black, orange. Sometimes I'll get confused and I'll add a number instead of the multiplier, but that happens. And I actually always test all my resistors just to make sure before I put it into a circuit. I test it on the multimeter. So brown, which is 1. We have black, brown. Black is 0, brown is 1. So that's a 1. Black is 0. This isn't a multiplier, but we're putting a 0 here because it's a number. And if it was the multiplier, we wouldn't put any zeros there. We multiply it, as we see here, we multiply it times 1. Any number times itself is times 1 is itself. Okay, and now here's our multiplier. We have an orange multiplier. So we have black, which is 0, brown 1, red 2, orange 3. So we put 3 zeros. And this is a 10K, 10,000 ohms resistor. And we'll be using a lot of these. Once we get into the microcontrollers and we deal with sensors and we do pull up and pull down resistors, we use a lot of 10K resistors as pull up and pull down resistors. And of course we'll get into that in a future tutorial. And this one is 22. And this one is 470K. I was hoping I pulled out a 470, but apparently I pulled out a 470K. Okay, now we have brown, black, and green. Once again, brown. Black is 0, brown is 1. Black. Well, let me make that a better one. Black, that's 0. It's the second. It's not a multiplier. So we actually put the 0 there. If it was the multiplier, we wouldn't put anything there. Green. Now we have black 0, brown 1. Let's do the rainbow. Red, orange, yellow, green. That gives me 5. So I need 5 zeros. 1, 2, 3, 4, 5. And what does that give us? That gives us a 1 million ohms resistor, and that's how you'll see it, 1 million ohms. That's the omega symbol. So that's 1 million ohms. So that's how we figure out what these resistors are. And like I said, if you need to figure out what the colors are for when you're looking in your parts bin, then you just go, if you're looking for 640 ohms, it would be, let's actually do the colors here. 6 is blue. And sometimes blue and violet are hard to tell the difference. And yellow is 4. So that's 6, 4, and we need 1 0, which is brown. So 1 0 is not black because this is our multiplier now. So that's brown. And pretend this is gold, and that's a 5. So this is our 640 ohms resistor. Blue, yellow, brown. Go look in our parts bin. Okay. Now back to our circuit. In Ohm's law. Now we're going to discuss Ohm's law. And then we'll start doing labs. We're going to do a breadboard lab. We're going to build this circuit that we keep drawing. 9 volts. Comes off here. Here's our resistor. Now I can put the LED here and then put the resistor after it. It makes no difference in what order I put these parts that you're seeing here. The resistor is still protecting the LED, regardless of which way I put it in. But since I started putting it this way, there is the symbol, schematic symbol for resistor. Now, our LED, if you remember, we were drawing them like this. The long leg is positive, short leg is negative. But we're going to do the schematic symbols now for our light emitting diode. Now what's funny is that's the symbol for a diode. But once we do the light emitting part, it's just a couple of little things like this. Of course those are little, I should probably use something, it's like a little light. That should actually look something like this. Depending on the schematics, I've actually seen it look like where people have drawn it like lightning coming off of these. But this is the symbol I see the most, and that's what these should be. They should have these little corners coming off for a light emitting diode. And then we go back to ground. So this is our positive, this is our negative, this is our positive, and this is our negative. Resistors aren't polarized. It makes no difference which way you put it in. LEDs are. So this would be the positive side, and this would be the negative side. So this is how we would put it in our circuit. Okay, now 9 volts is too much for this LED. We need to put a resistor in here. But how did I know to put a 470 ohms resistor in here? Well, that's where Ohm's law comes in. If you remember from our earlier video, and this is that little math I was telling you about. There is a little math, not a lot. We have V equals volts. R equals resistance. Sorry about that. And I will eventually get used to this drawing tablet. And I equals, in this case, we're just going to use milliamps right now. Most of our circuits are going to use milliamps. We're not going to go up to amps. So there's a couple of formulas we use for Ohm's law. I'm going to show you, there's 3 popular ones. There's a whole ton of them. There's a whole wheel that we could discuss. But we're only going to use the ones that are pertinent to what we're doing. So we're going to do 3 plus 1. There's the standard 3, which is volts equals amps. Actually, amps times resistance. Amps, I know it's I for inductance, equals volts divided by resistance. And resistance equals volts divided by amps. Or in our case, milliamps. And I'm going to get to how to do this math right now. So basically, if we have two of these, we can figure out the third one. Okay, so we have this LED. Yeah, we need a resistor. We don't know, but most components, especially when we get to integrated circuits, have data sheets. The data sheets tell you certain things. It tells you what volts you can use, how much milliamps it can draw. Let's assume that it says it can take 3 volts. And most LEDs can take 3 volts. But that does us no good. We have volts and volts. Volts and volts, we're not figuring out anything. What we need from this is how many milliamps it draws. How many milliamps does this little LED use? And in the data sheet for most of the LEDs that I'm using, these super bright LEDs, draw 20 milliamps, which equals 0.020. That's 20 milliamps. 0.100, that's 100 milliamps. 0.200, that's 200 milliamps. 0.001, that's 1 milliamp. 1,000 milliamps would be 1.000, or 1 amp. 1,000 milliamps make 1 amp. 900 milliamps would be 900. And like I said, 1,000, this would be 1,000. 1.000. It's important that you do this because this is what you need for the math. So these are your milliamps. And by the way, if I didn't mention it earlier, you want to start taking notes. This is where you want to start taking notes. You want this stuff in your notebook. You don't want to be searching through this video, listening to me telling you to write it in your notebook while you're sitting there waiting for me to do the math. You actually want to have this. Okay, so now from our data sheet, we know that this LED here will take 20 milliamps. So we know we have 9 volts, and we know we have 20 milliamps. So we need to know what we need to put here for a resistor. So we have our resistor here, which is volts divided by milliamps. I know that inductance drives me crazy. So we have 9 volts, and we divide that by 0.020. Hey guys, sorry for the interruption in the video. I reviewed it before I uploaded, and I noticed 2 simple mistakes that I'd like to correct instead of redoing the whole entire video. When we're discussing volts, let me get some color here. When we're discussing volts equals amps times resistance, amps equals volts divided by resistance, and resistance equals volts divided by amps. When I'm doing the math, you'll notice I say 9 divided by 0.020, and what I should have done was equals 450, and instead what I did was this, and I put 450. So the math is actually accurate, but this is wrong. If I was to do it this way, I should have did 0.020 450. So I apologize for that. It's just a small, simple mistake. The other thing I noticed was up at the little LED light that we had drawn, there's a plus here, and it looks like it's a plus here. That should be minus on the video. But anyways, those were 2 small errors that I noticed and I thought I would correct. Back to the video. So it's 9 divided by 0.020. Use your calculator. I got a calculator, I use it, which comes out to 450. So 450. So to get a perfect circuit, we would need, to use this at its max. Now, this LED will light up with less than 20 milliamps. It'll light up with probably a little more than 20 milliamps, because in the data sheet there's probably some tolerance built in. But it won't be as bright. So for its maximum brightness, you'll want 450, but it's not practical. So I chose the closest to it. Now, something I didn't mention earlier, it had to do with the tolerance, and I'm not going to get into it. Like I said, this is a practical course on electronics. With these tolerances, when you have a 470 ohms resistor, and I'm just only going to show you this once and briefly. The tolerance on a 470 ohms resistor is 23. Or we'll call it 23.5. We'll call it 24. So 470 minus 24 is 446. So our range can be 446 ohms. Remember, I was doing some of this earlier. And our max would be 494 ohms. So this 470 ohms resistor with a 5% tolerance could be one of these numbers. And usually what they do when they make resistors is they make them so they are outside the tolerance. So if you have a bunch of 5% tolerant resistors, you're not going to have a 470 ohms and a 450 ohms. You're not going to find a 450 ohms because it falls within this tolerance. You'll find it actually less than this, and you'll find it actually more than this. Now, I'm not going to get into this whole, I could show you in detail, what ohms resistors manufacturers produce with the different tolerances. I'm not going to get into that. That would be for another course. So basically here, we know we have 450 ohms resistors, and I can tell you this, you're not going to find a 450 ohms resistor. You're going to find a 470 ohms resistor. And you'll find resistor packs with a bunch of different values on them. So we're going to use a 470 ohms resistor here. And that light will work perfectly good with that. Okay, so that's how we used Ohm's law to determine the resistor that we need within this circuit. So if we have the amps in the resistance, we can find out what the volts are. If we have the volts in the resistance, we can find out what the milliamps need to be. If we have the resistance, if we have the volts in the amps, we can find out what the resistance needs to be. And to prove that, let's do a little bit of it right now. Okay, so now we have all three of these. So if we have the resistance and the milliamps, we need the volts. So we have milliamps, which is 0.020, and I'm using my calculator, so feel free to use yours, times the resistance, which is 470, equals, so we've got 0.020 times 470 equals 9.4 volts. Why isn't it exactly 9 volts? Because this isn't 50. If this was 450, it would be 9 volts exactly. But it's not. Okay. So we figured out our resistance when we had the volts and we had the amps. We figured out our volts when we had the milliamps and we had the resistance. Now, let's figure out from the resistance and the volts what our milliamps, what our draw on, what this guy is drawing on our circuit. And that's very easy. Once again, it's the math. It's 9 divided by 470. And like I said, feel free to equals 0.019. So we're supplying this, and in the data sheet it'll give you the tolerances. So we're supplying it, instead of 20 milliamps, we're supplying it 19 milliamps. So we're supplying it 19 milliamps and it's lighting up. If it was a 450 resistor, this would be 0.020. Okay, so you might be asking yourself, well, we have a 9-volt power supply. How are we getting 9.4 volts out of it? Now, there are ways to increase voltages, but that's not what we're doing here. If you notice, the math was based on 20 milliamps with the 470 ohms resistor. And we're actually only supplying it 19 milliamps. And so now that we have the correct milliamps, we would want to do 0.019 times 470, which is 8.93 volts. So when I was doing the math on this, there must be some more numbers back here for the milliamps. I only took I rounded it off to the first 3 here. So it's 8.93 volts. So we actually it's not, by using this 470 resistor instead of a 450, we did not increase the voltage to 9.4 volts. But we did the math based on the information we had. And when we determined what the exact milliamp usage was, then that gave us a more accurate voltage reading. So these are very important for our circuits. It's not hard math. It's multiplication, division, and use your calculator. That's what they were invented for. Students use their calculators all the time. Now, there's one more that, remember I said 3.1, or 3 plus 1? There's one more here that I want to add to this, just because it's a common question. I get it all the time from students, and they want to know the wattage. Well, what about wattage? You have volts, you have milliamps, you have resistance, but what about wattage? I see this 200 watt thing, or I see this, how do I figure out what the wattage is? What is the wattage of my draw here? Well, watts equals volts times milliamps. So volts times amps gives you watts. If you had 120 volts, that was drawing, let's say, 2 amps, you're going to have 240 watts. Or let's do this here. How many watts are we drawing here? Let's do something more practical. The 120, I was doing a household current, because you can figure out household current with this same value here, amps, volts times amps. But let's look at what we're doing. So our volts is 9 volts. And remember, we're not doing the 20 milliamps. We're doing the 19 milliamps. So ours would be 19 times 0.019, which equals 9 times 0.019 is 0.171 watts. So our circuit consumes 0.171 watts. And if you ever see those 1,000 watt, 1,800 watt hair dryers, you can just imagine what's going. It's 120 volts, and you can figure out the amps if you want. So I hope I covered this pretty well, because we're going to be covering this again in the labs. We're going to be showing you. We're actually going to be testing this theory, and these numbers are not going to look like anything what you see here. These don't take any of the tolerances into consideration, but you'll see that they'll be fairly close. They'll be fairly accurate. Let me see. Did I cover everything? I think that's going to be enough for one tutorial. Okay, thank you everybody. I hope you've learned a lot. If you don't, if you have questions, leave comments. I will respond to them. And the next video is going to be our first lab. We're actually going to build this circuit. And we're going to introduce a capacitor. One of the reasons I was showing you the capacitor is because we're going to introduce the capacitor in our next, in our lab. And we'll show it to you. There's not much to tell about the capacitor. There's two kinds of capacitors. Well, there's many kinds of capacitors. The two kinds we'll be dealing with are electrolytic and ceramic. These are polarized, and the symbol for them, take notes, break your notebook out, is for this electrolytic capacitor. And it's polarized, so this is actually the plus side, and this is the ground or negative side. And like I showed you over here, you can actually see, and actually you can see it a little here too. You can see one leg's longer than the other. Over here you can actually see the negative side. So when we put it in a circuit, and into the PNPs, you'll see the capacitors in the circuit as well. So when we put it in our circuit, this is positive and this is the minus side, and you'll actually see that in our live lab. We'll put that in the circuit. I don't think I need to do a whole tutorial on capacitors. They just store electricity. I will mention a couple of things about capacitors. They'll have ratings on them for volts, and you actually can't see the ratings on it. So maybe I will have a brief tutorial on capacitors after our first lab. And so you can't go over the rated volts. Most of these are like 30, 50 volt, and we're going to be supplying 9 volt to them, so it's not an issue. If you put these are the capacitors that if you put it backwards, they I don't want to say they explode, but they do. They pop their tops. Sometimes they smoke, sometimes they sizzle. You know, maybe we'll put one in backwards and see. You need higher voltages as well to blow them up. Even if you put them in backwards, they'll get pretty hot. And this, of course, is our LED, and as I mentioned before, the LED is a diode. There's a diode, like a power diode, and it's just got these two little things off of the side, and this is positive, and this is the negative side. Once again, this is the positive side, and this is the negative side, and there's a flat part here. And we'll go we'll go in detail in our labs with that. These guys, it doesn't matter which side. These guys, there's no polarity. It doesn't matter which way you put it in. You know, if you want all the gold to light up on the negative side, you know, feel free to do it. Actually, when I build some of my circuits, sometimes I do that just as a signature of my circuit. Trim pots, we're going to go into these in more detail, each of these legs. And I might even show you briefly in the lab before we go into more detail. Anyways, I hope you've enjoyed this tutorial on basic electronics, and I hope you join us for future ones. Thank you.